Okay. Hello, everybody. We are talking about the next chapter of Logiciel, chapter 4, which is about adding the topological part to this story that Cavia is telling us. So here's like just a mini recap of where we are and where this chapter is headed. So Cavia's basic narrative about foundations is that the orthodox or empty formalist notion of computation doesn't really help us think usefully about the brain or the mind, which is not really its focus for now, but mainly about just how computation is actually used and designed. And what we might call a more pragmatic theory of computation doesn't really defer the question of meaning or semantics as you would have in Tarski's way of thinking, which is the model theoretic semantics, which is like what the symbols mean is decided by a meta theory that's outside the theory, and that kind of goes on turtles all the way down. But instead, if you don't defer that, then we can have what Cavia would argue is a better way of looking at this, and also kind of transforms how one actually does logic and some of these other things. So what's happening here is he's kind of in this chapter talking about. So we touched briefly on the type theory stuff, but here he's kind of entering into the homotopy type theory, where the topological way of thinking comes in, which is a relatively recent development in the past couple of decades. So this is sort of my gloss on this, that there's a new and powerful candidate for immanent as opposed to transcendent meaning. And what that candidate is focused on geometric and topological reasoning, or the intuition that comes from thinking in geometrical and topological ways can be made formal. So logical proofs and programs have been shown. This is to be formally analogous to paths in spaces. So there's this Curry, Howard, Lambeck isomorphism that has proven very powerful, and a lot of the mathematicians and a lot of the CS people are pretty excited about it. So that's the main thing for people outside those fields, is you kind of feel the sort of palpable excitement of all of this. And these formal analogies create what I would describe as a kind of resonance among these different frameworks. So logic, CS, topology, and potentially other things seem to kind of help inform each other. So it's kind of different from the way that foundations were thought about in the 20th century, where you kind of do this sort of nitty-gritty axiomatic foundation work, which is kind of laborious, and then you get to a point where you just continue to do the mathematics as you did earlier. And you're like, okay, we've done the foundations, now let's move on. But now you kind of are, I would here, Cavia doesn't use this terminology, but I would say that what's happening here is that instead of a kind of ontological foundationalism, what we have is a kind of epistemological foundationalism. And even though foundation might not even be the right term, it's like there's a kind of conceptual scaffolding that you can use in a kind of context-dependent way, rather than starting with axioms. So we'll try and jump into how that pans out here. So this is how the chapter starts, with some things that are getting kind of famous in the math world, or at least this particular branch. So the late Fields medalist Vladimir Voevodsky outlined a new foundational project. And this article here from the Institute of Advanced Studies is quite readable. Some of the math will be kind of over a lot of our heads, but so he wanted a topological turn in theoretical computer science. It's kind of a reference to the linguistic turn that happened in the middle of the 20th century in philosophy, where everyone kind of went reflexively back into analyzing language, Wittgenstein being sort of a famous example of that sort of initiation. So Voevodsky underscored the success of set theory's appeal to human reasoning, singling out hierarchy as a key underlying intuition, while lamenting the expressive limitations imposed by the predicate logic. So there were things that you couldn't quite say easily, or they were a bit hacky to say. And this other thing is kind of well known in this kind of lore of how all this came out, that the informality of proof checking, including what we would think of as formal proofs, if you look at them, on the page, by mathematicians, there was a problem there, because proofs had been found to be faulty many years after publication. In fact, in Voevodsky's case, he had proved something that was sort of well received, and it got him, I think, into grad school. And then years later, he found out there was a mistake, and this happened a couple of times to him. So he started getting very worried about this, and interested in automated proof checking and interactive proof solving also. So these errors had in many cases led to a revision of significant conclusions, including, but instead of putting mathematics into formal correspondence with logic, an act only possible via encoding of both languages, Voevodsky conjectured a foundational system with greater expressive power, put around a computational kernel. So here are the three components. The first component is a formal deductive system. Language and rules for manipulating sentences in this language are purely formal. So in the Hilbert sense, that is pure syntax, just ways of doing things, moving symbols around. And that's what you need for a computer to be able to verify something. The second is the part that we've been talking about a few times now, that this idea of the semantics. So a structure that provides a meaning to the sentences of this language in terms of mental objects intuitively comprehensible to humans. So kind of having the best of both worlds. You want to both be able to allow a computer to check everything, and also make sure that the steps are intuitively comprehensible. So it's not just gobbledygook, like humans wouldn't be able to check assembly, for instance. So the third component is a structure that enables humans to encode mathematical ideas in terms of the objects directly associated with the language. So part of this chapter is about this notion of encoding, which I don't fully understand, but it's sort of, and I think the purpose of the book is to kind of just create a sort of suggestive picture for people who don't work in these fields. Yeah, so there's this kind of three waves of foundational thinking, if you look at the past 140 odd years, which is initially you had set theory as this foundation, which, as we talked about at the beginning, kind of solved a lot of people's logical concerns about calculus, but along the way created all this discomfort, which led to, on the one hand, formalism, and on the other hand, constructivism, because people didn't like some of the weird things about infinity that Cantor kind of made people confront. And then in the middle of the 20th century, you had category theory, which I'm sure a lot of you have heard of, which has a lot of overlap with type theory and homotopy type theory, but is a kind of alternative. And so homotopy type theory, which we'll talk about a little bit, is the newcomer here, and the most closely associated with automation. Category theory is more in the vein of abstract algebra, still done by humans. But in fact, on one of the category theory websites, they describe homotopy theory as a syntax to do higher order category theory, which I don't know whether this is like a slight insult or something like that. But so there's still a lot of flux in this space among the mathematicians and computer scientists. So a thought that came to me is, when you're outside of this world, like, what exactly are mathematical foundations? Why do we need them? Because it's like, if something has already been done, what does it mean to actually replace foundations with new ones? So I think that when you read what the motivations of the experts are, like Martin Löf or Voevodsky, it has much to do with the actual practice. There's very pragmatic concerns about what you can do. Right? So it's not just a philosophical exercise or being satisfied that you're on solid foundations, for instance. So so in this case, the theory of types of Martin Löf provides the means of encoding logic and mathematics into formal language. So we touched on this last time, that he worked through each of the logical connectives, showing how they have a perfectly intuitive semantics that you can understand, so that all the steps in a logical proof are meaningful. And so there's this correspondence in logic and mathematics, and that you can put into formal language. And Voevodsky sought to extend that into a fully fledged topological foundation, more rigorous and solid footing for mathematics, assured by methods of computational verification. So this research into homotopy theory, which is a branch of topology that kind of became its own thing, serves as an origin from which to erect new foundations with intrinsic geometric content. So this intrinsic, immanent, those are the kinds of things that often come up here. Is an attempt to build on the success of category theory, which remains the most complete post-war attempt at foundational mathematics. The question of foundations, often at odds with the emphasis of the working mathematician on applications, is in this case motivated by a new way of practicing mathematics. So that's what I was trying to say. It's kind of unlike a kind of earlier notion of abstraction, which is, oh, this is just philosophically minded or something like that. This is intimately connected with the actual practice of some mathematicians and increasingly lots of computer scientists, particularly those interested in functional programming and data types. William Lawver, yeah, he's really eloquent in talking about some of this stuff. There's some interviews cited here that worth reading. So progress on foundations is achieved by consciously applying a concentration of applications from geometry and analysis. That is, by pursuing the dialectical relation between foundations and applications. So I like that a lot. Although I myself don't necessarily do any of this myself. But it's sort of like there's sort of two philosophical attitudes you can imagine that relate kind of to both metaphysics and epistemology, which is to kind of have this totalitarian regime where everything resembling a contradiction is removed. And the other thing is to actually focus on the tensions and kind of build your system around tension, for instance, between the continuous and the discrete, or the computable and the uncomputable. And that narrative we kind of talked about before. But that tension is very productive. And I think what's nice about the debates in the 21st century is that more people are recognizing this. That rather than having these, sort of boring fights between, finitists and infinitists or whatever, you have this way of encompassing both. So terms that were once upon a time associated with Marxists or something like dialectics are showing up in pretty formal contexts now, which is an exciting thing. So yes, a topic that comes up here, which I've touched on a few times, is computational Trinitarianism, which I think originated in this blog post by Robert Harper, who's a CS professor. But it may I don't know whether it's earlier than that. So here again, it captures the excitement, which is why I like the quote. So the doctrine of computational Trinitarianism holds that computation manifests itself in three forms: proofs of propositions, programs of a type, and linking those two is the Curry-Howard equivalence, and mappings between structures. And that's what we'll get to here. That's the topological aspect of this, and the categorical aspect. These three aspects give rise to three sects of worship. We're making this analogy with like the Christian Trinity. Logic, which gives primacy to proofs and propositions. Languages, which give primacy to programs and types. And categories, which give primacy to mappings and structures. So that's the kind of algebraic side of things. The central dogma of computational Trinitarianism holds that logic, languages, and categories are but three manifestations of one divine notion of computation. There is no preferred route to enlightenment. Each aspect provides insights that comprise the experience of computation in our lives. This is what I can say about the resonance thing, which is that you're providing these equivalences not to then say, well, we'll just use this one side of the equivalence because that's the easy one. Each of them is actually providing some kind of new information that can kind of help you with your intuition. So here's like the excitement part. What I find captivating about this is it's beautiful. Imagine a world in which logic, programming, and mathematics are unified, in which every proof corresponds to a program, every program to a mapping, every mapping to a proof. Imagine a world in which the code is the map, and we're getting there slowly, I think, in which there is no separation between the reasoning and the execution. This is no difference between the language of mathematics and the language of computing. So even people who aren't at the forefront of math and CS would kind of enjoy this. Like I sometimes find that, like I wish I could just go from a circuit diagram to my simulation, but there's so many steps between them, and it would really be nice if that was the steps were fewer. Trinitarianism is the central organizing principle of a theory of computation that integrates, unifies, and enriches the language of logic, programming, and mathematics. And practically, this is the important part, it provides a framework for discovery as well as analysis of computational phenomena. An innovation in one aspect must have implications for the others. A good idea is a good idea in whatever form it may arise. If an idea does not make good sense logically, categorically, and typically, then it cannot be a manifestation of the divine. So yeah, there's this person I know, a Twitter friend named Pratyush. He's a designer, and he also makes these really good tutorials about lots of different science and math topics. And I asked him, can I use some of your diagrams just to get a visual feeling for this? Obviously, this one didn't really need diagrams, but where we're going with this is the idea of proofs and programs, which you kind of mentioned, and then this concept of paths, which is what will lead us towards the topology thing. So the idea that anyone who's done a derivation or a proof, a proof will know that there's a step-by-step aspect to it, and sometimes there's branching because you can go in multiple directions with a logical proof. And so that's like a path. So it's not a big jump to say, oh, look, this is like a path. And then you can ask, well, in what space am I moving? So because of these formal analogies, you can sort of import your way of thinking, carrying forward everything and without any loss into another setting. So unlike lossy projections like shadows, for instance, these are things that don't lose any of the information as you move from one to the other. Right. So the key idea with the Curry-Howard isomorphism is that not all programs that are equivalent to proofs, but it's the ones that are sort of well typed. They have a type structure. So the propositions are types, and just like data types that you'd see in programming. So in here. He's kind of building this up like step by step. So the rest of the book, I mean, up to this point, he hasn't really talked about this topological angle much. But what happens here is that if you look at, well, yeah, it's complicated, but it's there's this idea of path induction. So you can actually create paths linking different types. So in the resulting homotopic treatment of types, paths are primitives which precede intervals in space. So the paths come first, and then you can construct spaces from them, I think. Paths between two types A and B are function types. So you could imagine like something going from the reals to the integers, or from natural to natural, or something like that, which in turn can be interpreted logically as A implies B. And to map one type to another is to construct a new proposition as a distinct type. So you can make more and more complicated propositions by stacking up the way the types are.
So wait a minute. I mean, in the homotopy interpretation paths, the types should be equivalent. So it should actually be an isomorphism, not just a function. And
okay.
It's I guess it's not clear from this paragraph, but
Yeah, so he might be a little sloppy at some of these points. So good to catch those. Yeah, all the paths in are equivalences and identities and homo. So there's a sort of hierarchy of versions of sameness. There's like things that are like identical, like exactly the same element. Then there are things that you can sort of provably show are the same within the type. And then there are equivalences between types, and then you can generalize this to higher and higher forms of equivalence. So you get which you come across in well, yeah, in category theory, it's different because the morphisms don't have to be isomorphisms.
But I mean, to make this connection, like the proofs, like logic, computation, categories, like in a category, you don't need the morphisms, don't have to be invertible. And of course, in programming functions don't have to be invertible, and logic and implication doesn't have to be an equivalence. But I think, yeah, once, I guess I'm not quite clear, like based on what has been said so far, where that distinction of having it actually be invertible, which role it's going to explain in this discussion.
So this is something I myself, having been exposed to the homotopy stuff, I'm also not 100% clear on, which is that it seems as though just having equivalences and isomorphisms is like limiting, because a lot of the interesting things that we do are not isomorphisms. So and yet in order to construct mathematics, this seems to be something that is useful. So I don't know how much you can reproduce of all of computation using just this kind of thing. So yeah, but because the equivalences are between, well, yeah, I don't know.
I guess it would be nice to see where this focus on actual paths and equivalences is going to, how this is going to be part of the story, as opposed to just looking at the usual Curie, Howard, Lambeck correspondence.
Yeah. I don't fully understand some of this, but it's like I said, like kind of an ad for diving into this literature. So yeah, this is just a diagram of what a homotopy is. It's like so in a space, which for now we're kind of leaving abstract. It's like whatever notion of space you happen to have. This idea that gamma 0 and gamma 1 are homotopic if you can continuously deform one path into another. So these paths are generated between two objects on the basis of a structure-preserving transformation, which is what we were talking about. It's an isomorphism. So it's a very, very conservative mapping. To trace a path from A to B is then to demonstrate an isomorphic relation, which means you can go and come back without losing any information. To establish an identity between two objects, which simultaneously has a logical, algebraic, and geometric interpretation. So the geometric interpretation is this path idea. The logical one is one of the lists sometimes. I don't know whether it's just implication. Implication is asymmetrical. So yeah, there's three interpretations that you can have. So so where he goes with this is that there are two key acts in what he calls computational reason. So the aim of sketching out a topological model of computing which does not owe its semantics exclusively to existing mathematical ontology. So he's trying to sort of carve out what's unique about computation and not rely on earlier semantics, basically. I propose that there are two operations which can be described as definitively computational within this univalent view. So univalence is part of this homotopy type theory world. It's a little abstract, but so these constitute the type theoretic means by which okay, yeah, let's leave that part out. But yeah, so there's this. So the two concepts are encoding and embedding. So encoding corresponds to the assignment of a token to a type. So and that's the most primitive operation in type theory. So X is an integer, for instance. The second is embedding and corresponds to the generation of higher spaces via path induction. So this is a more complicated concept that I myself still have not fully wrapped my head around, but yeah, some suggestive analogies here, which we'll get to. So the two operations give us conceptual traction over the novel framework presented by Univalent foundations, distinguishing its account of computation from the canonical models. Moreover, this conceptual treatment will give us a means of uniting idea. Okay, so this part is interesting and I think a little speculative, but uniting ideas from statistical inference with deductive formalism to construct an integrated account of computational reason grounded in topology. So I think this is kind of going a bit further than what's in the very formal stuff, but he links this eventually to kind of this topological data analysis and so, the manifold hypothesis in machine learning, actually. And we'll get to that. So you could say that here he's kind of, again, kind of providing a manifesto of what he thinks computation is once you've built up this framework. We can see types as the most general application of the principle of encoding. Computing can be conceived in essence as no more than this. Quite simply, the science of encoding. So the examples that he provides, just sort of metaphors, I guess, are like encodings of data, so like JPEGs or MP3s. And I think the idea here is that data is not just like a bunch of ones and zeros. Like the file extension kind of constrains what you can do with the file. So putting something in a particular encoding is a way of sort of it entering into the space where it can then be used for computing. And so sort of the format in which you put something is the kind of key first act in bringing something into the computational world. Yeah, encoding is the act which renders any object computable. And the sense of encoding I am proposing encompasses the manifestation of programs in their entirety. Right, so here it comes back to his sort of criticism of the Turing orthodoxy. For close to a century, Turing orthodoxy has identified the computational with the machinic, the whole sort of physical mechanism idea. But what if computation is instead a more fundamental expression of form? Perhaps its true role is encoding logic into language and linking propositions to their structural, which is to say mathematical form. Rather than a universal machine enacting mechanical calculations, what if it were modeled instead as a means of navigating topologies? This is kind of the big kind of plan here. The elaboration of programs becomes synonymous with path induction in type spaces. And in this sense, it can be conceived of as an expression of the deep geometrical character of logic. So having made these links between logic and space, you can make that one more step and say all of computation involves moving around in a suitable space. And I think Andrew's point that if all of this is mainly equivalences, does it actually work? Because are there types of computation that don't map onto this is the question. I'm not sure.
Well, I just still not clear what role this the actual homotopical the focus, let's put it this way, has in the story, because there is you don't need homotopy type theory or path induction to have this Curie Howard Lambek isomorphism, and so definitely the role of this is not clear in the story.
Yeah, I'm not clear either.
At least, yes.
Yeah, Himanshu, do you have a suggestion about what is uniquely provided by the homotopy?
So as far, I didn't read until the Curie Howard Lambek stuff, but from what I got, it was what he was trying to get, what they were trying to get with homotopy type theory was, let me find that passage. It was, I'm going to look for that passage where there's discussion on this, but I think it's mainly like towards a more constructive sort of like methodology of doing computation. But let me see, there was a passage that describes it well.
So Andrew, what you're saying is that these equivalences between logic and type theory don't require the homotopy part, right? But
And,
yeah,
and category theory. So all of that was there before homotopy theory for the univalence.
right.
And I really don't, at least as of yet, don't see the role that this focusing on equivalence is having in the story.
I think it's like what they're talking about on page 123. Here we are interested in the role of recursion within a topological account, which will eventually lead to reframing of the creative subject in computational reason via a new model of automata guided by a pragmatically mediated notion of agency. What does a topological interpretation of recursion look like? And I think this is where they need homotopies. Like under univalence, primitive recursion is an isomorphism between an inductive loop on the natural numbers and any other such structure. So
Right, and then he has this diagram, which I didn't put it in here because I didn't quite understand what he was going for with this.
Well, again, I don't think you definitely don't need univalence foundations to have a topological account of recursion. I mean, any topos has a natural numbers object, so you can interpret Gödel's tier in it. That's at least as much recursion as you can do in piano arithmetic, so that's not bad.
so that might be something useful to explore. That might be a useful thing to explore, is like which is like, do we, exactly like what you said, like do we need homotopy type theory for, or univalence rather, for demonstrating recursion as an isomorphism between the natural loop and any other structure that has isomorphisms.
Yeah, I mean, I think the simplest thing is if you have any Cartesian closed category, so it can be, if you want, take like topological spaces that are compactly generated, or any of these Cartesian nice categories of spaces. If there is natural numbers object, you can interpret recursion there. And yeah,
Okay.
I haven't.
So I don't understand how these sorts of things wind up being isomorphic. I can see how they're. I mean, I just don't see. I don't see where I can see where you can generally map the natural numbers to the outputs of some recursive algorithm, right? But if I mean, if let's say the algorithm is just outputting a series of ones, I don't see how you can get the natural numbers back from that. Or am I just completely misinterpreting or misunderstanding this?
I think the idea is like, imagine a language in which you have natural numbers, and then you have, let's say, function types, product types, and maybe have sum types. So like,
oh, okay. So then you can, then you have the pairs to work with rather than just the.
Yeah, and so the thing is, you can interpret that in any number of quote unquote geometrical structures, right? The most concepts, most notions of spaces that we know of are like closed under these things. Well, I guess topological spaces are not actually nice by themselves, but still, I mean, a lot of concepts of geometric things admit those operations and types. So in fact, if you like write a program in a language like that, you can interpret that as a continuous function, as a morphism in some category of spaces. But yeah, I guess this is all kind of pretty old. So I'm curious where he is going with this.
Yeah, I mean, partly, I guess, absorbing the the excitement of the homotopy theory stuff, and assuming that that's the best way to proceed with.
Although I do have another question. Do any of you guys understand this what he's trying to get on this paragraph on the left side of the screen. This operation of assigning a token X a type A is somehow encoding. I mean, it seems that there is a lot more that goes in the notion of encoding than just assigning a type to a variable or a symbol. So yeah, what is he actually trying to get at here?
Yeah, that's a good question. I didn't fully understand that. I think it's the idea that you have some intuition about, which is like sort of before you put something into computational form, and it's like when it enters into the space of having a type, it's like, well, now it's the concept has entered into the space of the computation. So before that, it's not yet ready for, you can't really do anything with it until it has been
Okay,
given
and
a
so okay. Well, I guess then the thing here is it's not just the token being assigned a type, but it's like the actual idea of something having a type is supposed to represent some kind of comprehension of, I guess, what operations can be done with such things, or how such thing can be used, or how representations of such a thing can be manipulated, perhaps.
Yeah, that's a good point. So like when you're designing, like if you're coming up with a new type, like it's a difficult thing, because like you have like when we talk about examples of things, right? You have some specific examples, and then you want to put them all in one box together and say all of these are, of the same type. So I guess once you've done that, then adding another token of a particular type is not like, is that encoding? I don't know. In fact, that was one thing that it's a topic that I haven't really thought about much, is what exactly is encoding? Like we think about it like when something is already in the form of data and we put it into a different form. That's the sort of connotation that I have of encoding. But so what else is happening here? I'm not.
Yeah, and then the other thing is like the JPEG example of encoding is very different than encoding characters, because before you can even produce a JPEG encoding, you need encoding of the signal available to you, right? Like the JPEG encoding is a result of computation.
Yeah.
So it might be as I don't think it is the same type of encoding as a Unicode character. So
okay, well, I think maybe I have an idea what like the word I guess I would use here would be intentionalization, like when you create a way, a system of describing something, like if you have that, then you have you can say that you have a type for things, like you can have representations of things that can be computed with. But I still don't quite I guess agree that this I would not identify that with the concept of context extension, or like the fact that you declare a variable having type A. I think is a completely different kind of mental operation than what I would call intentionalization, which is providing I guess an encoding a way to encode things into some kind of representation language.
I agree. So I think what's happening here, because I got this the second time I read the book, like while I'm reading it now, I picked up on something which I didn't fully notice earlier, which was that the Cavia wants to kind of create this computational world that's sort of completely self-contained, right? This whole idea of immanent meaning and not having a meta theory means that he's like very opposed to like even referencing the physical world on some level. So it's as if the first act has to be something that's sort of already in the computational world or in the program. And so anything beyond, like this is a couple of pages in this book, in this chapter, that I found quite mystifying, which I think come from this unwillingness to talk about clearly he is absorbed Martin Löf's kind of idea that, you know, these things should have a semantics, but like on some other level, you always need like the physical world, or like things that are not quite language and logic to ground the logic, right? And which is why it's not so easy to dispense with transcendentalism, right? The idea that there's some that something else other than the formal system justifies the formal system. I think he's tied himself in knots because of that. I'm not sure though. So yeah, so if that was a bit weird, I think even embedding is even weirder. I actually asked him, aren't you, if he could make any sense of this, because it's like kind of going further in this direction using this topological idea. And this example is also quite strange. Embedding is no simple isomorphism, but rather the act of inducing a path in an attempt to embed propositions or types in a higher space. So here again, I think he's not being strictly like in the homotopy space, because they're not isomorphism necessarily. If we take a space containing paths between two concepts, wetness and rain, the space itself represents the judgments which take the form of the function type. Rain implies wetness. So yeah, he's doing something strange here. He's trying to kind of construct larger and larger propositions, as one does in logic. But I don't know that. Yeah, I'm not clear exactly on what the path perspective gives you here. So yeah, and he's making some link with this homotopy level, which I don't completely understand. But it does. Yeah, so maybe I just have to dive more into the homotopy stuff to maybe learn a bit more about that. And here he kind of is where he jumps into this notion of a notion of embedding from machine learning. So, which I think a lot of us are familiar with. The embedding allows us to develop our inferential perspective to integrate modes of statistical inference, in which projections of the sort described above are known as kernel methods. So this is that idea of like moving into a space like word2vec or something like that. The domain of machine learning has a canonical theorization in terms of a manifold embedded in the space. Interpretation, okay, yeah. So this is like the kind of popular idea that's coming up a lot in machine learning, which is that you live in this manifold and that there's some meaning associated with either movement in that space or like distances in that space, as in the case of word2vec. Right, so again, this is again kind of a speculation, but sort of sounds reasonable. The act of embedding is analogous to learning the latent space of relations within some input data. It's kind of what's happening in the statistical case, but is that the case for the more formal stuff? If you're extending paths to be higher order paths, it's not entirely clear to me. So, oh yeah, so I get this is sort of a strange chapter, but we come back to this. This is earlier in the chapter. He was talking about recursion as an isomorphism, and I'm not entirely clear on what's happening here, but I think here there's some sort of philosophical point being made about self-reflection. So it actually reminded me of Hofstadter and strange loops. That seems to be what's happening in this page and the next one. So yeah. So I guess this is exactly what Hofstadter does in Gödel-Escher-Barth, right? Indeed, it was Gödel who sought to formalize recursion, having explored its capacity to burst logical frames of reference. So it's that sort of going back in the loop. And here, I think there's an interesting point, which is not exactly related to computation, but more kind of to do with self-consciousness. So Negarestani is a philosopher. He discusses a recursive mode of self-reference in relation to a Hegelian notion of subjectivity, offering the schema I to I star, in which concrete self-consciousness acts as the identity map of formal self-consciousness. I think what this means is that you make something explicit. It's almost like the only way that you can attain self-consciousness is with a model, which is definitely not identical to yourself, but it's the only thing that you have. So it's like this process of like, yes, I have nothing else, but like the map is not the territory, but the only way I can make anything out of myself is via maps. I think that's what's happening. Self-relation enables intelligence to treat its own structure as the intelligible object of its own understanding. So it's a lot of like, snake eating its own tail kind of thing. Yeah, so I guess this is speculative, but not too wild. As such, recursion is the prime mechanism by which the emergence of a subjectivity within computational reason can theoretically emerge as the instantiation of an inconsistency, which I think again is sort of like this self-referential paradox idea.
Wait a moment. So what is this inconsistent multiplicity of being? Is anybody familiar with that?
This is straight from continental philosophy, and I'm a little baffled by this. Manju, you read this, right? Do you have any thoughts on this? I have some vague ideas about what's happening here, but
let me read this again.
But yeah, so I think again it's this desire to create a completely internally consistent, self-contained notion of computation means that how you got there in the first place is sort of a mystery. That's how I read it. Yeah, but beyond that, it's the that sort of philosophy that I don't fully understand anyway.
I mean, I guess a lot of people, kind of fantasized about like along these lines, like again, like Gödel Escherbach was talking about strange loops and Gödelian loops, and wasn't it? Yeah, who was saying that the Gödel's theorem was kind of proven that we cannot have AI because computer cannot jump out of the loop, but the human beings can because of quantum physics. I think Penrose was making some stuff like that.
Does Chaitin say things like that? Maybe Penrose is. Yeah, I find like all these arguments quite absurd. But Penrose actually, that's one of the reasons he was interested in that quantum consciousness stuff. Why I don't see it, but here's how, this is my version of that. What I think is the issue here, that whenever you actually make a successful formal system, there's a certain rigidity to it compared to whatever state of mind you're in prior to making one, because there's a sort of flexibility that we have, so we can make consistent systems, and we can make them extensible, or we can make them formal in this way, or constructive and inferential as the constructivists like. But like we can make inconsistent systems too, either accidentally or intentionally. So that I think reflects back on the nature of mind, because if in a strange way, I don't know what else one can say about it.
Well,
other than the flexibility.
Yeah, but I mean, this has often been made, this connection that like consciousness is kind of having a kind of like symbol for itself that is like whose interpretation is the self, and but I guess it's a little bit I still wonder how he got from like computation and path induction to like aporia of eternal recognition
as I put this at the end of
perceptive unity of inner sense.
It's, if you read Negarestani, it's a longer book, so there's a bit more elaboration along these lines. But yeah, that's why I put this at the end, because I didn't really know what to make of it. And I think it's possibly that he's tried to squeeze too much into like just a very short discussion. That's how I see it.
But this idea of the fact that we can supposedly make formal systems that are consistent and then somehow jump out of that system to imagine like a stronger system that is still consistent. It's I mean, still nobody gave a good I guess argument for why we are not a system like that. I mean, a consistent system like piano arithmetic can still reason formally about an inconsistent system, like you know, like enumerating all the proofs of you know, piano arithmetic plus, you know, plus 0 = 1, for example. I mean, you can still reason I guess about inconsistent systems in a consistent fashion, right?
Right. Yeah, that's true. That's true. Yeah.
I think one of the like things that the author is trying to do is to position computation as a central, as one of the central subjects of like thought, which the author is worried maybe in a sense that when people think of philosophy and thought, computation generally isn't like the first thing that may come to their minds, right? They're usually thinking metaphysics or mathematics or something like that. And what the author is trying to do overall in this book, I think, is carve out a space for computation as as a central subject for things that we otherwise relegate to like metaphysics or mathematics.
Well, up until like the 90s, it was pretty, the computational theory of mind was pretty popular, but
it was a computational theory of mind, but it wasn't a it wasn't a sort of like it was still like mathematically like founded,
as opposed to, so he's trying to separate out the computational from the mathematical and have it be its own thing,
like
right?
like even for example neural networks, like the neural network theory of the mind is a mathematical theory, not a computational theory, right? Even though neural networks are written as programs, the description is mathematical. We talk about dynamical systems, right? We don't talk about programs, for example. And I think one of the sort of at least one bent of the book seems to be that the author is saying that there is a lot to be gained by thinking everything in terms of in a computational framework rather than a mathematical framework or some other metaphysical framework. And
right. So,
therefore now trying to bind all the other ideas people have talked about, for example, like Badiou's ideas of multiplicity or whatever, to things that are familiar in the computational framework of recursion, right? So that's I think what is the attempt over here, which is all of these things that philosophers have talked about, trying to bind them to things that sort of like are hallmarks of computation that are considered as opposed to like mathematics, for example.
That's a good point. So yeah, that's actually, I think that's the right way to approach this because I was thinking before that I should do a little like thing on Hegel and sublation, but the first thing to think about here with this unity business is actually there's this paper by Wilfrid Sellers about something called the myth of the given, which is this idea in philosophy of mind, sort of, which philosophers often get really hung up about, is like whether there are atomic facts that we have access to in the mind, that they are intrinsically already have the structure of facts and that they are primitive in some sense. And a lot of people would say no, and that paper was trying to argue that we don't have facts, we can construct facts, but whatever it is we're given don't have the structure of statements. So it was this whole line, partly because of linguistic philosophy and partly because of this computational way of thinking, to think that what we receive from the senses have the structure of facts or like assertions, like the idea, kind of in David Marr can kind of glimpse this, right? Which is this idea that this pixel here being red is equivalent to something going on in V1, which is equivalent to the predicate pixel XY is red, and so there's this problem here that people have, which is this doesn't quite work out. There's something sort of paradoxical about starting with the idea of that facts are what are given to you. And for neuroscientists, this is sort of, or at least for a lot of us, never assume that the things that are coming from the retina should be considered like logical facts or Boolean or any of that sort. Some people still do think of it that way because the information processing metaphor of the brain also kind of goes in that direction. So that's one.
Wait, is the issue like how sensory data and other kind of data becomes propositional or like logical, and is they, I mean, so why would you want it to be? I guess my question is like, do people believe that it should be that somehow the logical level should be able to account for everything? Like, why is that?
Yes,
why is that the goal? Like
Jerry Fodor was the most. So Jerry Fodor had this computational theory of mind and representational theory of mind, and his idea of what the base level representations were modeled on language. So and he was also interested in his own way, kind of somewhat similar to Cavia, but which is the idea that it's almost dualism, right? It's like the idea that to study the mind, we don't have to talk about the brain at all. We can start with some primitives, and those primitives are facts that are the types of things that can enter into propositions.
Well, this sounds like Wittgenstein. The world is all that is the case.
Yeah, exactly, 100%. So there's a direct line from early Wittgenstein through this logical positivism to Fodor, I think.
Okay.
So maybe a little bit like less representationally speaking. I mean, I think anyway, like even from the dynamical perspective, we can think of things like bifurcations as computations in some sense. So I don't know, these are the kinds of things that I'm interested in, like whether the structures of these sorts of things map to any sort of like any of these structures that are coming up in this book or anywhere else. So
yeah, that would be nice. And it seems like the more traditional topology of dynamical systems is the place to look for that, and then find out if there's a mapping from there to something more like logic. Because like when they, what is all that stuff? Where they like the Smale map and all of that. And then there was like, what is it called? Symbolic Dynamics, which is where you kind of classify the state space into different qualitatively distinct types, and then you can do computation on it, if I remember correctly, like in the sense of digital kind of computation. I don't remember the details, but it for some reason is also related to chaos theory. But yeah, I don't know about that. So the other sort of, oh yeah, so the other this unity idea is again sort of a weird thing that relates to introspection, which is for some people it is completely obvious that everything that I experience is unified by a viewpoint. Like I have the central viewpoint from which everything is unified, and this leads to all kinds of weird paradoxes, right? Because it's like, well, if everything's converging onto a point, like imagine if like all the information in the brain were converging on one neuron. As soon as it reaches that one neuron, all the distinction of the different types of information gets lost in the integration of the single neuron. The integratedness of the different pieces of information can't really work by some literal-minded physical bringing things together, or at least no one has figured out how that could possibly work. So yeah, so I think that's what's happening here. This is the kind of continental way of saying this, right? That the apperceptive unity of inner sense, like how I would translate that is like the fact that all these things that are happening to me, you know, and that I can link them all together, is a purported unity which suppresses a fundamental inconsistency, an abyssal fissure in being, which puts in motion the concretization of intelligence. So I don't know exactly what's happening there, but it's almost like it's the separateness of all the different things that allows you to kind of allows things to interact. So that's where the autonomy of these things comes in, that they're not all kind of integrated, maybe. And that's, I think, how you get to this kind of reason cleaving from the mind.
So can this idea be tested on like I don't know, something more primitive than or more complex than a human mind? Like I don't know, like does an ant colony have a single point where all the information that it's knows, so all the data that it receives about where, or maybe like the bee's colony somehow integrates information about where the flowers grow and where like the temperature and so on. Is there a kind of integrating process, and does it come together at some point?
So I will look into the ants and bees. I suspect the answer is no, but this is what Giulio Tononi and gang are trying to do with integrated information theory. They purport to say that you can, like, given a network of interacting entities, you can ask which subset of them is the most integrated, and wherever, like, it's sort of like you take the power set of all possible combinations of entities that you're interested in, and whichever of those the subsets like is most information integrated, that is the level of that entity is conscious, and nothing at a higher or lower level. They motivate it by phenomenology and introspection, but it doesn't answer this question of whether the information is all brought to one place. In some sense, I don't think anybody believes that, but it would be interesting.
Well, also, I don't think the author suggests that the information is brought to one place, right?
Right. In fact, I think that's it's sort of criticizing this apperceptive unity of sense.
Yeah.
And so it sort of, so what you said earlier about is, I think, appropriate, that there are some ideas that have been floating around in philosophy, and now that there's this, well, right now in the past 20 years or so, there's been a sort of analytic and continental philosophy are coming a little bit closer together and willing to talk about each other's stuff a little bit more, especially on the continental side. So
I would expect the author and whatever is said in this book to support rather that the unity is not given, right, and it's built by us.
Yeah,
so
yeah, okay.
Even in the case of the ant hill, if we demonstrate that there's a unity, that's something that we are building. That's not there, right? And I think that's the idea. as opposed to claiming that the unity exists and then, showing it. The idea is it doesn't exist until we actually have built it.
Yeah, so this is definitely a kind of hallucination in the middle, just in terms of the way it's written. But because like I kind of get it. I find it funny almost now. This Lyotard's discussion of the machinic unconscious highlights precisely that which is missing in the regime of organizational, namely any escape from the despotic addressability of the given. That's what I was talking about, the myth of the given. A hermetic panoptics of inscription that renders the unthought unthinkable.
He should be a poet, because you should read this more like a poet.
Yeah. I mean that's true of a lot of continental philosophy. But so yeah, as Badiou notes, the unconscious is that object which does not fall under a sign or concept. So this is, I think, almost like a cliche now, right? This idea that there's all this stuff that we don't yet symbolize, and we don't know how to. And intuitionism is like, and is always on the edge of that, right? This idea that there's some stuff which I'm not bothering to symbolize, and it is from there that I get the stuff that I did symbolize. It's working around that. It's like that paradox of like saying the unsayable, like there's the ineffable. So the temptation here maybe is to just dispense with that entirely, in the same way that the intuitionism and constructivism specifically dispenses with the actually existing infinity. So we could say that from the perspective of ontology and the mind, that the unsymbolized unconscious is like the actually existing infinity, something that you can actually dispense with. I'm not convinced that that's possible, but I think that would be consistent with Cavia's constructivism, maybe.
I think it may also be consistent to just call that a false identity.
Say it again.
The unconscious, whatever infinity or whatever you're calling it, right? The unsymbolized space. Even labeling it as an infinity is sort of like a false identity, right? You're giving it a unity that doesn't even, or a totality doesn't even exist yet, right? And
because you haven't constructed it. In fact, philosophers have made this claim about the apparent oneness of perception, or like people have talked about the binding problem, right, in the mind, which is like, how does everything get bound together? And obviously there's going to be someone who says, is it in fact bound together, even in experience? Which I like, my intuition is definitely not that. So I find it amazing that people think this, but it's cool that you can ask, because it's perfectly consistent with the constructive philosophy, right? Like if you make a claim about something being unified, you have to show it. But how that works with self-evident claims, I don't know, because even in here, and not just with Cavia, with other like Per Martin Loff's treatment of truth, right? There's like judgmental equality, and what's the other one? There's two kinds of equality. But like, what's the other one?
Propositional.
Propositional, right? I can never remember which is which. So one of them you can actually prove. One of them involves proofs, and the other involves.
That's the propositional. Actually, it's best to, I think, to call them judgmental or definitional equality and logical equality, because the first one is like actual syntactic identity, like two things are the same. In fact, it's more like the judgmental equality. It's more like equality at the level of descriptions. You can transform one description into another through computation or through a finite sequence of transitions. Whereas the logical equality or propositional equality or equivalent equality, it's the thing you actually prove. It's the thing for which you actually construct evidence for, that you need to construct evidence for. As opposed to the judgmental or definitional equality, it's somehow more basic. It's really at the level of representations. in some sense that the two descriptions can be computed to the same, to be syntactically identical.
I find all this very interesting and very confusing because even here, as it turns out, this is quite a difficult problem inside mathematics to automate what constitutes sameness. Like I was reading about, maybe Andrew, you know about this. What's it? Some sort of elimination, which is it makes proofs simpler.
The elimination rule for the J.
Something like that. No, but it's called something else. There's a which so far none of these proof assistants have. It's a way of like making lemmas basically, where you can sort of have this proof that's somewhere else and then invoke it later on. And it's there's a term for it. I'm completely blanking on it. And apparently, so far this has not been automated. In these proof checkers. So what I'm trying to get at is the idea that even when we've made all this progress with I mean, because obviously type theory is an open research project, but the idea that a thing that often happens in a proof is, swap out one thing for something that's the same as it. And not all of that can be done automatically. You kind of have to, from the outside, say, yes, these two things are the same.
Yeah, but I think that's more like, I don't know, I guess I'm opinionated on this because I think that's more like the fault of language design or that some of the issues in designing this language are still not fully solved. Because really there is, I mean, if you just follow the basic type theoretic methodology, there is no problem. I mean, if your language is Church-Rosser, then two things which are judgmentally equal or definitionally equal can actually be computed, have a common, reduct. And if your language is normalizing, which in this case corresponds to consistency, right? If you have a consistent language, then you can just normalize both things to check whether or not they're exactly the same, because any two descriptions will eventually reach a normal form. And so I think that's, I think that there is kind of the generic type theoretic design principles would that you wouldn't consider conversion proofs having actual logical content. Like really that two things that are definitionally the same, you don't write about, like when you write a proof, you don't write about that. For example, I think in our Archimedes had like some proof where I don't remember if it was approximation to pi or if it was like computing the square root or something, where it was just at some point it was clear that there was that you could approximate a certain value, and so then immediately the conclusion was like, oh well, therefore this value is between like 22 sevens and like some other bound. So like the mathematician who knows an algorithm, which at that point was already like public knowledge, it was part of the scientific record of humanity that you can compute this thing. So once you have that needs no more elaboration. Right. If you, for example, if you write a proof and somewhere in your proof you need to know like that the square root of like cube root of 19 is within like this particular epsilon, you will not actually write the computation in the proof, right? You'll say like take out the calculator and you can. So I think there is. I definitely think that there should not be any secondary witnesses, as Voivodsky called them, or any like additional proof terms for conversion proofs. Two things are convertible. That means that need not be elaborated further. That is left to the reader or the computing agent or the proof checker, whatever is your, whoever is doing the processing this proof.
Yeah, okay. So basically, it's just a matter of making sure that all of type theory, ironically, gets encoded or gets implemented in the language, in the proof checkers and all of that. Yeah. So yeah, so
I
yes.
guess I have another question about this conversation though. So what exactly is this unity that is getting, I guess you're saying, is somehow being dissolved, the side sounds of being like being made unnecessary by this computational point of view. Can you elaborate on that?
Who was it directed to?
Whoever would like to talk about unity. I still don't fully understand what he's getting at, but I think it's about this binding problem kind of thing, that there's unity in multiplicity in experience, which is that there's many things happening, and they're all happening to me, to one person, in some like sense. But what that sense is difficult to make clear. And many people start from that assumption, more in the philosophy side than in neuroscience, because we're not at the point where we can actually do anything in neuroscience that could show that. So some people who are who have a very kind of formal idea. In fact, what's his name? Like the sort of naive empiricism of the early, like Hume. So David Hume, for instance, he had this very simplistic idea of what perception was. It's like we just get information from the world, and that's it. Like, and that's what's in our heads. So the idea that there's much more to it. So that it kind of, to say that we're picking up information from the world, you might want, it's kind of equivalent to saying that whatever you pick up is already in a format where it can take part in thought. That's how I would put it. And maybe that's why encoding is a relevant concept. So like, in what sense is a photon part of your thought? In no sense at all, right? But once it has made contact with the cell in the retina, it has translated into the language of spikes, let's say action potentials, right? And now it's like, it can participate in what is happening in the brain.
But that language is not a language of the body, it's a language of our model of the body.
How would you distinguish the two? That's the thing.
It's so, like, I think a good example is when people model, say, for example, a visual system as neural networks, right? What is the input coming as? It's coming as a vector, right? So that is just a mathematical model. It's not a biological model of the input, right? I mean, nobody actually has gone and checked whether this is actually a true vector space, right? That, and that this is the vector is represented in a nice basis or whatever that is going to this neural network. Like, nobody does that check, right? It's all sort of like assumed and taken for granted in a way. And that's just brought in by the model, right? It's not brought in by the physical nature of the body. At least we have not even shown that it is. We're just assuming it is. Does that make sense?
But are you talking about a biological model or an artificial model?
The artificial model of the biological entity.
And so when, that's the difficulty, right? When is one allowed to say, like, what are you allowed to say about the nature of the input to the actual biological system?
Yeah. So, and I think that's the thing. You cannot make that statement, right? And
cannot make any statement.
Yeah, and it
has
which
I think is part of the point of this in some way. These 2 pages here.
Yeah, but it's like, it's not even limited to the computational view. It's just like, even if you're not taking a computational view, if you're taking a mathematical view, you still have to do the encoding.
Encoding of what?
Of the physical phenomena to a mathematical object.
Ah, yes, okay, yeah.
Or if you
It's a little bit like,
if you have a physics model, which is still, somebody may say it's a mathematical model, but let's say it's a physics model, you still have to then translate it to a physics object.
or like for instance, I'm looking at, or like take a map, right? I'm trying to navigate by a paper map or a map on my phone. I need to register where like my perceptions of where I am with some point on the map, right? So, and then when I can move around on the map, I'm like, I don't know whether I've encoded or not, but it's or like when I want to.
The encoding is done by instruments there.
Yeah, or if I want to like predict the movement of Venus or something, right? The movement itself is in some kind of qualia space, if you like, which has no characterization. So then I convert it into like some azimuth and whatever elevation and this
right.
and that.
And then from there you predict where Venus will be, and then to demonstrate that it actually works is when the Venus is there, you take the new encoding of Venus and say that the two encodings match, right? And so we do this in other things as well. Point of the book is that all of this is computational. We view it as a computational thing. So like we are inherently just computational beings. And what we talk of as, say, empirical science or mathematics or whatever, all those things are just different facets of that computational existence. I think that's what the book is trying to say.
I think so, yeah. So yeah, and it's like the part that's the speculation is that the path idea is going beyond just equivalences and homotopies to just paths in general. There was a good quote.
I think the point about the qualia space is crucial, though. I mean, that does seem to me that's where everything grounds out for humans, is there's some sort of qualitative experience we can't describe, and that's where it grounds out. And so if you're ignoring that, then you're sneaking in what to me seems like the ultimate grounding that, at least for now, we have no way of really describing.
Right. So that is my default way of approaching things. And so what's kind of fun for me about this book is that it's so not that, because I suspect that from the perspective of Cavia and the other sort of computationalist maybe, is that they don't want to refer to the qualia space. They think of it as another example of the transcendental. So it's a little bit like in the olden days when scientists would refer to God or something. So like the ultimate arbiter of truth becomes something that is not represented at all, which I'm okay with. But some people find that difficult, because I think that's what's happening here, like with this strange poetry at the end, the despotic addressability of the given. It's like, is everything that's given to me addressable? And by that I mean, does it have the form of the symbolic? Not really, because there are so many things that I cannot make explicit. And so you are left with the choice of being like kind of like a mystic with respect to that, or to try to banish it, which I think is what is happening in this book.
Mm-hmm. Yeah, like does qualia need to be embedded in a space?
It cannot be, or at the very least, it has not been. And so here's how I would interpret this. And maybe I'm being very charitable because I agree that this is very unclear. I think of what's happening with this I and I star, this Megalistani thing, is like this, that I would like to convey to you something about my qualia. How will I do this? At best, I will recruit some symbols, which I myself know are inadequate, and they're only a map and not the territory, right? And then I will iteratively go through different maps and then see where we go from there, and then do that again. So it's like the best you can do. So it's like the finger pointing at the moon, right? Like we like to say the finger pointing at the moon is not the moon, but I had no other way of pointing to the moon than to use the finger. And in this case, it is all the symbolic.
Yohan, could you repeat that? I'm trying to understand what you're saying, but it's not quite isn't quite clicking for me.
I'm just like kind of spitballing here a little bit, but I think it's like let's take Tarski's way of establishing the truth of logic as like a microcosm of the metaphysical problem. Okay, so Tarski's way of establishing the truth with model theory, etc., is to say that all these formal symbols have no meaning, and then outside of that we have a meta language which decides what the meaning is. And then you have to just do that over and over again. Well, in the metaphysics or the philosophy of mind, what you're saying is that all the symbolized acts that we engage in, all the talking and math and computer science, etc., is only grounded in this qualia space, which by its nature has never been symbolized. Like it's always outside the domain of the symbolic. So it's even worse than Tarski's meta theory, because at least the Tarski's meta theory is in symbolic form. So some people are okay with it. I would say, I don't know, I have no idea what the numbers are on this, but a fair number of people are okay with the idea that there's some ineffable grounding for the effable. Yeah.
Isn't there like a functional role semantics where basically you can just say that ultimately the symbols are grounded in some kind of like computational procedures which need not have any logical content to them at all?
So yeah, I guess he's trying to, Cavia in this book is trying to skirt around this issue by having the cake of semantics, but also the logic part. So so what exactly is functional role semantics, and how is it different from?
Well, I don't know. Maybe that's not the right name for it, but my understanding that you could always imagine that the grounding problem is solved by just like the atoms of the lexical entries, whatever, are just some kind of computational procedures which are not. Which are no longer linguistic or symbolic in themselves. I think
that seems to be. It may be along the lines of what Cavia is doing here.
If they're not linguistic or symbolic, how are they described, Bevo?
Well, yeah, I guess. I mean, okay. I really. I guess silly example could just be that like machine learning, right? Could have some kind of a neural network isn't actually doing any reasoning, a logical representation or anything, but it just sometimes tells you it's a cat or it's not a cat, and that's kind of the lexical entry for cat is that some part of your brain says yes, like it's not or no.
Yeah, but
not saying yes.
But I think the thing with the neural network is not a fully independent system, right? Like something else is actually telling it what cats and dogs are.
Yeah, but it's not like, yeah, you definitely
like without that external like scaffolding in a way, it wouldn't be able to tell a cat from a dog, right? And that's like the ugly duckling problem, right? So the
okay.
Now I see why Hegel is cited here. So what was Hegel's game, right? So like it's like okay, a quick tour of German idealism, right? It's like Kant responds to Hume. Hume says everything is just all these basic perceptions, and Kant's like, this is nonsense. But it's hard to explain why exactly it's nonsense. And Kant puts a lot of effort into this to say that everything that we construct is a construction of the mind, and that that if there are things in themselves, we have never said anything about them ever. So thing in itself is no thing, right? And then then you have Hegel coming along and saying, okay, Kant, you've done this good work of showing that there are no things in themselves, and yet you mention them. Can we simply dispense with the things in themselves and say that there is just this one entity that is kind of getting to know itself, and that is spirit or Geist. And by that, he doesn't mean anything supernatural. It kind of just means the historical sort of almost cognitive Sprachbund, like the all of us are the space in which all of us are able to speak is the only thing that exists, and that there is no bunch of things outside. It's very like intoxicating in a way for some people to have this type of monism. It's a pure idealism, right? But at the same time, it seems to make surprise and mystery impossible. Or so it's like you get to very ancient Greek ideas, like nature loves to hide. So in this particular case, it's like
why is it
hiding from itself.
Why do you think it's making surprise impossible? I think. Okay, sorry. Go ahead.
No, I don't. That's just my intuition.
I think surprise is still possible, but not in the way that you would have constructed in the older way, right? Here, surprise comes through this process of self-realization, right?
Yeah, that's totally what Hegel's up to.
And that's in a way sort of like what some of this thing is talking about, right? Like it's the inconsistency arises through this recursive process, if you look at it from the computational sense, like so. Yeah. So if you replace, things like the word inconsistency with surprise, as the way you're talking about, right? That's sort of like the message that's been talked about here.
Right, I can see that now, because if you go back to Brouwer's choice sequences, etc., you're kind of attributing a random number generator to the observer on some level, rather than to some transcendental entity, which is why Brouwer always talks about the free, the constructing subject, the free or the imaginative, creative subject, the creating subject or the creative subject. Mm-hmm. And at that point, like when you are the first person constructing a procedure or constructing a real numbers decimal expansion up to a point, in some cases, it's almost as if you're pulling it out of nowhere or of yourself. So yeah, it's one way of thinking, but it still makes it like it's like the process of Hegel's spirit is like nothing has been made explicit, and then in the process of making things explicit, surprise happens. And so yeah, I don't think it like actually.
It's a very specific form of surprise, right? It's not the sort of so surprise in the sense that it's not like the jump scare sort of surprise, but more like a new realization that was not expected by
which is like to bring it to this, like it's closer to what happens when someone proves something, because like if you believed in that axiomatic formal system where everything is just already implied in the axioms and the logic, then there's nothing surprising because everything's a tautology, right? Everything is just a consequence of what you already started with. That's not really how people feel when they make a formal discovery. So yeah, you can kind of recover a form of surprise there, I guess. So yeah, I think that when you want to make everything immanent and avoid the transcendental self or the transcendental objects in themselves, you end up coming somewhere. And I mean, you probably say it in different ways, but it's something like this, which is that.
Well, I mean, so you could imagine if this is all like if all this computational, thing is running in some kind of like. Just imagine a programming language with like a very expressive type system where you can have like effects and co-effects. So you could have like types in which the programs of that language are also represented, and the kind of a program that is analyzing its own source code and the reasons about it, and you can also have like types for different environmental models, and so you can model in different interactions with environment. So in that sense, you could imagine like a computational process that sort of reasons about its own self, like its own relation to its environment, without any Tarski like transcendental thing out there at all. It's just a pure process. But I guess what I understand is that like is that like the computational theory of mind, or is that like what he is trying to get at? Because what's the difference?
I think the author is definitely trying to get at that. I don't think that is what is a traditional view of the computational theory of mind.
Why not? What's
because of his generative nature, right? Well, like what the author is trying to say that yes, that's what's happening, though all the types are continually just being generated over time, that they're not existent in totality at the beginning.
But why does computational theory of mind assume that they are like existent totalities at the beginning?
Because generally, go ahead.
The computational theory of mind is not based on type theory, so it's at a much, and it's mainly a philosophical theory which is operating at a much more coarse grain, at best referring to just Turing machines. So and sometimes logic and sometimes Chomsky style linguistics. So it doesn't actually make contact with this ampliative, like this idea that you can make new data structures.
It doesn't really talk about even in the sense of the Turing machine, doesn't talk about that the tape is constantly extending itself. Right, that it generally assumes that the tape.
Yeah, but I don't know. I still like don't see like what's the big difference though, right? I mean, if you can think that all our experience is a kind of computational program, I mean, it's kind of almost like a then the viewpoint where there is no like transcendental kind of reference for anything, where all the symbols, all the reference, and ultimately to like other processes that we can kind of.
So I actually think of this as a transcendental theory.
Okay.
Because there is sort of like expansion that's happening in our ontology over time, but internally through this type proliferation.
Okay.
It's a different sort of transcendence, but it's still transcendence. It's not yeah. So
the connotation. So in fact, I guess that's the sort of tightrope of walking in between these two things, which is that traditionally kind of formal systems are sometimes thought about as just like shuffling a bunch of symbols. And people have even said this about reality, right? That reality is just permutation of like the basic things that already exist. So that there's nothing new in the world, it's just permutation. And the connotation here, I think, is what Himanshu is talking about, that there's like build-up of new types and new propositions.
And that's the mode of transcendence that is provided by this theory.
And also the emphasis on contingency.
I don't know. It all seems though very much in a like a pretty simple computational framework. Like I could imagine, like having a language where there is a program that like generates this types and it analyzes how admitting them into the type structure could affect its execution in the future, and to do like all kinds of reflection, like self-reflexive, basically have this a completely internal construction of like objects and relations and types, completely just internal, like and interpretability between all these levels can all be internalized actually. So I guess that's what I mean. I guess that's what I always thought, like the computational view of mind would look like, but and I'm not sure what else.
Yeah, and I
it
think
could be.
so. That might be. I feel like that's for you. You see it naturally that way, but like if you talk to like, say for example, somebody who is more used to like a machine learning or deep learning or a neural network perspective of the mind, right? People who are doing AGI using neural networks, whether they will see it that way, right? That
Or like people who are not involved in like, because like Fodor, for instance, the guy would say like, to hell with the brain. I think there's some quote like that. Because the goal was like, let's just stick with inside the domain of the computational, specifically to talk about the mind. But then obviously the issue becomes, and it's going to be an issue here too. If like in the early parts of the book, he tries to constrain and say like, I'm not doing a full-fledged metaphysics of everything in reality, and because he's not actually drawing a line between what constitutes non-reason, or like he focuses on computational reason, but what about perception? You know, what about action? You know, those things. What about the physical world? Like those things don't fit into this. So it's sort of saying that all those things may be happening, but like it's sort of like a control room where it's almost like necessarily true, right? That the only things that can enter and leave the control room are things that are of a certain format. You know, they have to be computational, and to enter into that space anyway. When they leave, then like it's like as if we form representations of things that are non-computational and non-mental. By virtue of what we've inferred from the results of our computation, which is a weird irony, I think, or something like that. But it's like it's like that version. It's like solipsism or something. I have a belief in the external world because of subjective private experience. So yeah, it's. But I do think that what you were saying about sort of completely internal self-reflection of a program is what is kind of advocated here as if not a theory of mind, then a way to reformulate philosophical ideas that have been around for a while, such as these Hegelian ideas.
Okay, well, so that makes sense. Like I can totally get behind this project. I mean, the idea seems kind of natural.
Yeah, it's like a little bit old wine in new bottles, but the idea, partly inspired by this Trinitarianism business, is that if you successfully get people to buy into some of these analogies, then they transform how you think. So it's not simply a matter of re-establishing Hegel or something. It's like it's almost like if you get a critical mass of people who know a little bit about this stuff, interested in the more philosophical, speculative stuff, new thoughts about the relationship of mind to other things might emerge. That would be the relative part of this book. I'm going to stop.
Okay, well let's continue because it's like almost half an hour.